This is 8.5. We're going to be looking at factoring. We've looked at adding, subtracting, and multiplying polynomials, and now I'm going to get into factoring, which involves some principles of division here. So property is always try to pull out the GCF first. We did talk about that with finding the greatest common factor and dividing that into each term. Pulling that out, factoring it out is what we've called it, and writing the polynomial so that the GCF is listed first with what's left over from the factor tree listed in parentheses. And so just as a review here, the GCF of this first polynomial, we have a binomial here. If we think about our factor tree, this factor is 2 and x, 16 would be 4, and 4, which factors is 2, 2, 2, 2. So we have what's in common to each of these? Well, looking at the first one here, we have a 2 in this one and a 2 in this one. The only other factor in the first term is x, and there are no x's in the second term. So our GCF in this case is 2. We'll write down our 2. And if we divide 2 into 2x, or look at what's left over at the bottom of our factor tree, we have a factor of x. So you'd get it if you divided 2x by 2 is x. And if you divided 16 by 2, you would get 3 2's left over, or 2 times 2, which is 4, times 2 more is 8. So it's 2 times x plus 8. So that is factored so that the greatest common factor has been pulled out. Let's do that with each of the next two here. We've got 18y cubed. So think of this as 9 and 2, and then we've got y times y times y. The 9 factors is 3 and 3, so we're looking at right here. This is our bottom portion of our factor tree. That's our roots there. And if I do the same thing for 12y, I have over here 3 and 4 and y, and the 4 is 2 and 2. So the bottom layer of that factor tree has 4 factors in it. It has a 3, 2 2's, and a y. Whereas over here, the bottom layer of 18y cubed has 2 3's, a 2, and 3y. So start identifying things they have in common. I've got a 3 here and a 3 here. I have a 2 here and a 2 here. I have another 3 in the first one, but not in the second one. I have 1y here, 1y here. And you'll notice that there aren't any more y's over here in the green factor tree. So my greatest common factor is the product of one of the sets of factors I've circled in red. So you'll notice I've got a 3, 2, and a y circled in the blue factor tree, and a 3, 2, and a y circled in the green one. So I just pick one of those sets of factors, multiply it together, and that's my GCF, or greatest common factor. So 3 times 2 times y is 6y. And so I'm saying that 18y cubed minus 12y, that polynomial, it's actually a binomial, can be rewritten as 6y times something. So the something is what's left over in terms of factors from each of these factor trees, or we can think of it as division. I'm really taking 18y cubed and dividing it by the GCF 6y and placing that term here. So right over here in my factor tree, I see what I'm going to end up with. I have a factor of 3 and then 2 y's, which is 3y squared. So I have in parentheses here 3y squared, and then minus, I'm just copying the minus sign you see right here, the factors that are left over from the green factor tree here, which is just 2. And so my greatest common factor is 6y, and I'm left with 3y squared minus 2. So 18y cubed minus 12y is equal to, in factored form, 6y times 3y squared minus 2. All right, let's apply the same principle down here. We've got 4, 4, and an m and an n, and those are 2, 2, 2, 2. And so let me circle this bottom layer. We've got 4 2's and an m and an n, and this one would be 4, 5, m, and the 4 can be 2 and 2. So let's circle that bottom layer as well. We've got 2 2's, a 5, and 2 m's. And over here, the 8mn squared is 4 and 2, and this is 2, 2. and we've got an m and two n's. So let me circle those factors. I've got 3 2's, an m, and 2 n's. So I'm circling them just so we don't lose any factors or get confused with the previous row of the factor tree. So let's see what we have in common here. We'll do that maybe in black this time. We've got a 2 here, and a 2 here, and a 2 here. And it looks like I have another 2 in each one. And then I don't have another 2 in each of these. I have one in the blue one and one in the green one, but not in the red factor tree. So 2 2's that are common. No more 2's, so I can go on to the m. Looks like we have an m in each one. And I have an n in the blue one and an n in the green one, but not the red factor tree, so that is not common to all 3 terms. So in black, I have 2 times m, which is 4m, and so that is my GCF. Let's see what's left over here. I've got in the blue factor tree 2 times n, which is 4n. I've got a plus sign in between. You can see the plus sign right here. In the red factor tree, I have a 5 and an m left. And I have the minus sign. I'm going to copy down the minus sign. In the green factor tree, I have a 2 and an n left. So that's 2n squared. So that is factoring out the GCF. That's what we look for first. We always want to look for our GCF first, and then we will move into other methods of factoring the polynomial further, which we'll talk about today. All right, trinomial factoring, 3 terms. We have 3 terms, x squared plus 7x plus 10. That is a trinomial. It's 3 terms. The process for factoring that, we start by looking to see, does it have a greatest common factor in any of these? If I were to do a factor tree for this, you'd see I have x and x, 7 and x, and 5 and 2. And you'll notice that there's nothing that all 3 have in common. And so that step being done, I don't need to worry about that. I'm done with that. I can't plot a GCF. I'm going to go into finding 2 binomials in this case that can be multiplied to equal that trinomial, x squared plus 7x plus 10. Now we have many different techniques. Most textbooks have a couple of different techniques, but one is to kind of go backwards from FOIL. You're trying guess and check. You're trying to figure out what outer and inner term would add together to equal 7, and last term, and also give you last term or last terms that would multiply to equal 10. We have a way of just visually organizing the data as we go about factoring, and there are many graphic organizers that can be used to help us in factoring. But here's one of them I'll show you today. So we have, it's called the big X. We're going to multiply the front and back numbers to get the top. Now when I say the front, there is an unwritten 1 in front of the x squared. So when I say the front and back, I'm talking about the 1 and the 10, the number in front of the x squared, and what's called the constant term. So we multiply front and back numbers to get the top. So the top here is 1 times 10, which equals 10, and that's going to go right here on the top. So we're just telling ourselves that we're looking for 2 numbers that multiply to equal 10, and they have to add to equal something else. Let's go ahead and figure that out. It says in number 2, the middle number goes on the bottom. So the middle number is the 7. It goes on the bottom. So we are looking for 2 numbers that multiply, so we're right here on step 3, multiply to get the top number and add up to get the bottom number. So kind of a little math game here. These 2 numbers in this case will be your factors, and they will go in the parentheses. So and that's as long as this number right here in front of the x squared is 1. But we're looking for 2 numbers that multiply to equal 10. Now, if I'm really going to understand, I can't assume that every trinomial is factorable. If I'm going to make sure that I find the one unique set of factors that work here, I need to be able to list all factors of 10. And so part of this process is listing all the factor pairs. What I like to do is start from 1 and itself, start from the outside and work in. You can start from the inside and work out. It doesn't matter, but 1 and 10 are factors of 10. Then we move up to 2. 2 and 5 are factors of 10. If I move up to 3, 3 doesn't go into 10 without a remainder. 4 doesn't go into 10 without a remainder. 5 goes into 10 2 times, and I'm back where I started. So there are only 1, 2 factor pairs for 10. 1 and 10 and 2 and 5. And the question is, of these 2 factor pairs, do either of these add up to 7? The answer is yes. There is a pair that adds up to 7. It's 2 and 5. And so 2 and 5 are the 2 numbers that you're going to place on the sides here, 2 and 5. And so once you get to that point, you have figured out what numbers will be paired with x so that we can write x squared plus 7x plus 10 in factored form. And so what we're saying is x squared plus 7x plus 10 can be rewritten as 2 binomials being multiplied together. The 2 and the 5 go here and here, and they can be switched. We have an x here, an x here, and a plus here and a plus here. The signs go with the 2 and 5. And you can actually check these by multiplying using the distributive property. Let's just check it here. X times x gives me my x squared. X times 5 would be 5x. We call that the outer term. The inner term of FOIL, 2 times x, is 2x. Notice that those two add up to 7x to give me the middle term. And then finally 2 times 5 are the last terms, and they multiply together to give me 10. And so if you can multiply these 2 binomials together and get your original trinomial, you have factored it correctly. Now some students can just use guess and check, and they already know that there's going to be an x here and an x here, and so they're thinking, okay, what 2 numbers multiply to equal 10 and add to equal 7? And some students can do that without having to use the big X. But the big X is a nice visual way to organize our work, remind us of what we're looking for as we're factoring what we call a simple quadratic. This is a simple quadratic. And we're going to extend this process to not so simple quadratics next time. All right, let's see if we can go ahead and look at all the different combinations. We got factoring if all are positive, factoring if the middle term, or b, is negative. We call the middle term the b term. We'll learn more about that later. And factoring if c is constant, we call the last term c, or the constant term of a trinomial. So in each case, we can use our big X. Our goal, of course, is to rewrite this as a product of 2 binomials. Now, let's think about what we know for sure. We know this has to be x, this has to be x to get x squared. There's no other choice. This has to be plus, this has to be plus, because we have all positive signs in here. And so really with this big X, all we're doing is trying to find 2 numbers that multiply. Let's see if I can do the same color coding here. 2 numbers that multiply to equal the last term, 15, and add to equal the middle term, 8. And so once again, I'm going to list all the factor pairs of 15. I think it's really important that you can list all of them, because there may be a case in which this is not even factorable, and you wouldn't know that unless you've listed every possible factor of 15 and none of them add up to equal 8. We kind of get lulled into the fact that, yeah, all these ones I've given you are all factorable, but as we go to solve quadratic equations by factoring, it may be true that it's not factorable, and you won't know that unless you've listed all the factor pairs. So if we got factor pairs here, I don't want to make it look like a factor tree. Let's do this. So we've got 1 and 15. I'm working from the outside in. 2 doesn't go into 15. 3 does 5 times. 4 doesn't. 5 does, and I'm back where I started. So there's just 2 factor pairs, 1 and 15, and 3 and 5. And now we're looking for the factor pairs that add up to equal 8. You'll see that 3 and 5 work. Okay. So my factors here, let's go ahead and fill it in. We know that a positive 3 works and a positive 5 works. And we already know that the first terms equal x squared. The last terms give us the 15, so we've checked first and last. Do the middle terms really give us 8x? Well, look at this. 3 and x is 3x. 5 and x is 5x. 3x and 5x add up to 8x, and so it all checks out. So it doesn't hurt to do the check. Ultimately, what we're looking for is what I just have here. It says x squared plus 8x plus 15 equals, okay, I've done the check, erase the diagram here for the check, equals x plus 3 times x plus 5. So it's like taking the number 15 here and saying, okay, well, 15 can be rewritten as 3 times 5. That's what I'm doing. I'm taking this trinomial and writing it as a product of two binomials. All right, second one here. Let's go ahead and draw our big X. We are looking for product of the first number. Remember, in each of these, the first number is 1. It was up here. It is here. So we want a product of the first number and the last number. The first number is a 1. Last number is 24. So 1 times 24 gives me 24, and they have to add to equal, this time, negative 11. See the sign here, negative 11? We're going to carry that sign with the middle term. So I'm going to list all the factor pairs of 24. There are more of them here. Starting at the edges, we've got 1 and 24. 2 goes into it 12 times. 3 goes in 8 times. 4 goes in 6 times. 5, no. 6, yes, and I'm back where I started. So this has 4 factor pairs. Now the question is, do any of these add up to or have a difference that gives me 11? In this case, we're looking for 2 that add up to give me 11. Here's why. I know that when I go to factor this, I'm going to have an x and I'm going to have an x. Now, in order to get a product of 24, positive 24, circle that again, but a sum that is negative, the signs on this are going to have to both be negative. So I could go through here and I could put negatives in. They're going to have to both be negative to add up to negative 11. So I left that out when I wrote the factor pairs, but I can see that based on the fact that the two numbers must multiply to equal positive and add to equal negative. That's always the case when b is negative. So, and c is positive. So as I look through my list here, I've got 1, 2, 3, 4 factor pairs. There's only one factor pair that adds up to equal negative 11. It's the negative 3 and the negative 8. And so I'm going to carry those signs with it and write them here, negative 3 and negative 8. And you'll see that if I distribute here using FOIL, I get x squared minus 8x minus 3x plus 24. And these two in the middle do actually add up to negative 11x. Right. That's when the middle term is negative and the last term is positive. So we looked at positive, positive, negative, positive, and now this is positive, negative. So once again, just draw my big X here. I'm looking for factors of negative 15, two numbers that multiply to equal negative 15, add to equal 2. And let's fill in what I know so far. I know this is x, and this is x. In terms of signs, I don't know yet. We're going to figure those out right now. Let's go ahead and write all my factor pairs of negative 15. So negative 15 could be, well, when I bring that negative into it, it changes things. It could be 1 and negative 15, or it could be negative 1 and positive 15. Both of those multiply to equal negative 15. The next one is 3 and negative 5, or negative 3 and 5. Both of those also multiply to equal negative 15. So those are all my factor pairs. You gotta keep in mind that a positive times a negative is a negative, and that's what needs to happen for these factor pairs. So I can take a factor pair like 1 and 15 and consider it in two different ways. Either the 15 is negative or the 1 is negative. Same thing with the 3 and 5. Either the 3 is negative or the 5 is negative. That gives me 1, 2, 3, 4 factor pairs, and only one of them will work here. I've got to find one where the bigger of the two factors in absolute value is the positive one. So looking at these two, 1 and negative 15, that first one, that's a difference of negative 14 if I added them. Second one is positive 14. The third one, 3 and negative 5 have a difference of negative 2. It's the last one on here, negative 3 and 5, that actually multiply to equal negative 15 and add to equal 2. So I've got x minus 3, x plus 5, carry the sign with it. If I check it, I have x squared plus 5x. This is using FOIL at first, outer, inner, last. The inner product right here is negative 3x, and then the last term is minus 15. And we'll see that when I combine the outer and inner, I get plus 2x and then minus 15. So it checks out. So that's factoring what we call a simple quadratic.